This is Mr. McCord's chemistry class, Unit 9. We're going to look at assignment number 2, colligative properties of solutions. So up to this point, we've been looking at how we can measure concentration of solutions of something in something else. So like what we're dissolving, we call the solute, in the solvent, what's doing the dissolving, to make the solution. However much of our solute is in the total amount of solution or the amount of solvent can tell us how concentrated it is. Concentration can be related to a number of properties of the solution, like how conductive it is or how acidic or basic it is. But we're going to look at something a little bit different here for colligative properties. So first off, colligative properties are just properties that depend on how many particles of your solute are in your solution. So you can think of colligative properties being about the collection of solute particles. So when we dissolve something to make a solution, we end up with a uniform distribution of those solute particles in the solvent, and the quantity of those particles affects how extensive that property is. But to get more specific, one thing we'll be looking at is boiling point elevation. So as we dissolve more and more particles into a solvent to make a solution, we change the boiling point. It actually doesn't stick around the usual. So if like water boils at 100 degrees Celsius, typically at standard atmospheric pressure, then as we dissolve stuff in that water and make it more and more concentrated, full of something else, then our boiling point goes up. So we kind of end up changing how much energy it takes to get our particles to change from the liquid phase to the gas phase. And we'll also look at freezing point depression, where our freezing point is lower than the usual for that specific solvent, like water typically is what we'll be using. And again, because this is colligative, the more particles we have, the lower our freezing point gets, just like the higher our boiling point gets. So these two properties are going to stray from their usual for whatever solvent we're using, again, typically water. To kind of focus in on boiling point elevation, whenever we have a group of water molecules, like for a solvent, we get a liquid to boil when we get them to a high enough average kinetic energy, so a high enough temperature, get those particles moving fast enough to escape, to fly away, to break out from the attractions between the other molecules. When we put in and dissolve a solute that is non-volatile, which means it doesn't evaporate, it doesn't boil along with the solvent, it just kind of sticks around, then it basically blocks those water molecules or solvent molecules of whatever type from escaping. It makes it harder for them to get out. So you can think of this as like if you've got a defensive position in football that's making it harder for the offense to make it past them, or if you are on a crowded bus and you are trying to find a way off of it, and everyone's kind of moving at once. Whenever we've got something dissolved in there that is not going to boil with the solvent as it kind of increases in energy, then we're going to have it become harder and harder and harder. In other words, our temperature is going to have to become higher and higher for our solvent to really start boiling. So the more particles we have in the way, the higher the boiling point has to be to get those solvent molecules to break free and escape and get away from everything else. Okay, so down here on the left, we've got an example of what our water molecules might look like as we've got particles kind of escaping from our solution from a liquid to a gas. And we've got that boiling process reduced on the right when we've got some other particles in there, the green and blue guys, kind of floating around blocking and getting in the way of those water molecules trying to escape. So we have to have a higher temperature to get those water molecules to bust out, therefore a higher boiling point. Now we can calculate just how much the boiling point is going to raise by with a couple things. Since this depends on how many solute particles are in the way, we want concentration to be a part in it. And we also have a constant, just a number that goes with the specific solvent. So to kind of go through this left to right, this delta TB is the change in the boiling point, right? Or in other words, it's how much the boiling point is elevated by, how much it raises by. If you remember that triangle, that Greek letter delta just means a change in something. In this case, it's not just a change in temperature, it's a change in the boiling point of what we would usually expect. So how much is the boiling point going to increase by? Okay. The Kb is a constant, right? It's just a number that belongs to whatever solvent we're using. So for water, we will have a specific number that we plug in every time we do this for water. If we used a different solvent like isopropanol or ammonia or benzene, then that would have a different Kb value. But as long as we know what the solvent is, it's just a number that we plug in. And then the little m is molality. It's just a measure of concentration. We use molality in this case because it's not dependent on temperature. With molarity, increasing or decreasing the temperature can change the volume of a solution a little bit. So a solution can become a little more or less concentrated depending on how hot or cold this is. Since we are going to be increasing the temperature of something to get it boiling, we want it to be independent of that temperature. So we use molality, which is based on the mass of the solvent, not the volume of the solution. We have similar things going on with the depression of the freezing point. So going the other way, when we lose energy from the solvent, our particles freeze. In other words, they kind of collect together. They get close to each other and kind of become rigid in place and just kind of shake. When we have a low enough temperature, a low enough average kinetic energy, everything starts moving slower and slower and slower and slower until they're stuck next to each other. Okay. Again, in the same kind of way as with the boiling point, having particles of our solute in the way of those particles trying to freeze, trying to stick together and slow down, is going to make it harder for them to group up and form that kind of repeating structure of the solid that it's used to. So going from a liquid to a solid is going to be harder if you have other random particles in the way. Okay, so again, you can think of the bus example. If you're trying to sit down on a bus that's already packed, then you're going to have a hard time finding a seat, when everything's kind of already taken. If there's a big old empty bus and you can just sit wherever, and then you've got it free and clear. So in order to get things to freeze when there's a solute in the way, we have to lower the freezing point. We have to have a lower temperature. We have to get everything cooled down even more than usual to get them to settle and to get that structure of a solid. We also have an equation here for the freezing point depression. So again, our delta TF is how much the freezing point is lowering by, how much kind of colder our freezing point has to be. So delta TF just means what is our freezing point, how much is it going to be dropped by. Kf is another constant. It's also specific to the solvent, but it's for freezing. So even if we're working with just water, we have a different Kb for boiling than a Kf for freezing. So you got to be careful. Those are two different numbers. Okay? And again, the little m is molality. The same measure of concentration whether we are doing freezing point depression or boiling point elevation. Okay, so here's kind of a summary of the math that we're looking at. Again, we've got our delta TB or delta TF as how much our change is for our boiling point or our freezing point. And again, our boiling point is going to go up as we need to get this stuff hotter and hotter to get it to boil. And the freezing point is going to get colder and colder as we need to get everything chilled out more so everything kind of sticks in one place. You might find online or in a textbook that Kb and Kf have some fancier names. You can say that Kb is the ebullioscopic constant, or if you don't want to be a nerd about it, the boiling point elevation constant. And Kf is the cryoscopic, or again, freezing point depression constant. Again, both of those just depend on the solvent. And then in both cases, little m is molality, moles of our solute divided by kilograms of solvent. So when we go through example problems with this stuff, it's all really just going to be a little bit of algebra. Sometimes we'll have to get a little bit crafty with it, but for the most part, these problems aren't usually too bad. So in this example, we've got antifreeze, or ethylene glycol, that lowers the freezing point of water by 45 degrees Celsius. Okay, so we've got this compound, this ethylene glycol stuff, C2H6O2, that when mixed with water is going to make it harder for it to freeze. We're going to have to drop the temperature more and more and more. So in this case, our change in freezing point is 45 degrees Celsius. That's our delta TF. Okay, we want to figure out what the molality of that solution would be. And we also want to figure out how much the boiling point would be elevated by using that molality. For our solution of ethylene glycol, we know that the freezing point has dropped by 45 degrees Celsius. That's what this delta TF is there for. So we're going to plug that information into our equation that relates our change in freezing point to how concentrated this is, using this constant here. Okay. Now we don't know the concentration. The molality is what we're trying to figure out. But as long as we know what this is being dissolved in, we have that Kf, all right? That's the freezing point depression constant. So you just go look this up. I usually have it on a reference sheet or on the worksheet, directly right there for you. So the freezing point constant for water is going to be 1.86. And the unit for that is degrees Celsius per molal. All right, molal means molality, molal concentration. It's a concentration. So this is saying that for every mole per kilogram of solute to solvent that we have kind of dissolved in here, our freezing point is going to change. It's going to drop by 1.86 degrees Celsius. So if I want to solve out for this molality here, I've got to get molality away from this. So we've got to divide this off. So I'm dividing both sides by that 1.86 degrees Celsius per molal. So this whole thing goes away. It's just going to be molality over here, and then the glare on the board is kind of getting in the way of this other number. But this is going to be 45 degrees Celsius divided by 1.86 degrees Celsius per molal. So my degrees Celsius unit is going to go away. And then the unit I'm left with is molality on the bottom of a fraction on the bottom of another fraction. So it's going to flip up to the top. Okay, so I'm going to wind up with the unit of molality, which is what I want. Okay, so to finish this, I'm just taking 45 degrees Celsius divided by 1.86. My calculator tells me that my molality should come out to be 24.19 molal concentration. Now, this can be a little confusing. The unit for molality, instead of writing moles per kilogram, a lot of times is this little m, which is also kind of the same thing as what we have for the variable here. So don't get those mixed up. We don't need to cancel those out from both sides. We're saying the molality is equal to this much concentration. Okay, so sometimes our little m, the variable, will be replaced by a different letter like b or C, whatever you want to use. But in this case, I'm just going to write it like this in a different color. So our molality is 24.19 molal concentrated. Now we also want to see how this solution would also have its boiling point increase. So it's not like this works only one way and not the other. It's got to go both directions. So I've got my molality, my concentration of my solution. I can just go and apply that to this equation here. Whether, I'm trying to figure out something about the freezing or the boiling, it's the same concentration in the solution. Okay? The only difference is going to be how that boiling point or freezing point is affected with this constant. So there is a different number for boiling compared to freezing. So, in this case, I want to figure out what my boiling point is going to increase by. And to do that, I need to plug in the constant for this that I already know and the molality that I just figured out. So I'm plugging in my molality. All right. And if I go look up the boiling point elevation constant for water, that comes out to be 0.51 degrees Celsius per molal. Okay. And this algebra is even easier to work out than the last one because it's already pretty much set up. We just have to take this times this. Our units, degrees Celsius per molal, times molal should cancel out very nicely. They'll just go away. So my delta TB is just going to end up being these two numbers multiplied together. So 0.51 times 24.19 is going to come out to be about 12.34. Unit is degrees Celsius, and that's how much my boiling point is raised by, is elevated by. And that's my answer. So, circle that. Go ahead and circle both of them so it's a little more exciting. In this problem, we are adding salt to some boiling water, and we expect the boiling point to rise as a result. We want to know how much it's going to rise by, so we want to calculate the elevation of the boiling point, that's delta TB. We are already given the amount of moles of the solute, the salt that we're putting in. And we've got the mass of the solvent, 1.5 kilograms of water. So if we can use that to calculate the molality of the solution, then we can further take that to calculate the delta TB. In this example, we've got 1.12 moles of salt dissolved in 1.5 kilograms of water. So if we want to figure out just how much our boiling point is going to increase by, okay, we're going to need to figure out the molality first. The Kb is just a number I can plug in for our solvent, water, right? So the only other piece missing is this little m, the molality here. Well, molality is moles of solute divided by kilograms of solvent, and I've got that already right here. I just need to take my 1.12 moles of sodium chloride and divide it by that 1.5 kilograms of water. So I get my calculator. 1.12 divided by 1.5. I get 7.46-ish or 7-ish, depending on how you want to round. 7. So this is a 0.747 molal concentration of solution. Okay. Now, since I have the molality, I can take this a step further and solve for my delta TB. Right? no matter how concentrated the solution is or what temperature it's at, the Kb for water is always going to be the same. So I just plug in my Kb for water from before, 0.51 degrees Celsius per molal. Now I will multiply that to this concentration I just figured out, 0.747 molal. Right. Get my calculator again. So 0.51 times my 0.747, I get about 0.381. Right? And my unit is going to be, my molality there. My per molal and my molal units are going to cancel. So my unit here is going to be degrees Celsius. So my boiling point goes up by only a fraction of a degree, 0.381 degrees Celsius, not that much. Okay? Now, if you were doing a problem where you had to figure out what our new boiling point was going to be, you just take your old boiling point and add whatever this is. So for water, our boiling point in Celsius is 100 degrees Celsius. If it increased by 0.381, then our new boiling point would be 100.381. Some plants will actually get sweeter in the winter as they increase their concentration of sugar, like glucose, to resist dying of frost. So as it gets colder out, a plant will kind of resist that cold temperature and that risk to damage the plant by producing more and more sugar inside the leaves, which to us make it taste sweeter. Not all plants do this, but you can find lists online of frost-tolerant plants like spinach. So there actually is a little bit of a change depending on when you buy it and where it's growing and what the temperature is at that time. So in this case, we've got 5 grams of glucose. That has a molar mass of 180.16 grams per mole. Right, and it is dissolved in 0.01 kilograms of water. We want to figure out how much the freezing point is going to depress by for that sugar solution that we've made. In this case, I want to figure out how much my freezing point is going to depress by decrease by, using this amount of sugar that is dissolved in this amount of water. So again, I'm going to need to figure out the concentration, the molality here, before I can figure out the freezing point depression. But I'm also not given moles in kilograms, I'm given grams in kilograms. So if I want to calculate molality, which is moles of solute over kilograms of solvent, I'm going to need to convert this to moles. So just a 1 fraction bar conversion. Okay, so let's set that up. Now, in most cases, I would need to add up the molar mass of all the stuff in this compound. In this case, I am told what the molar mass is, so I have a little shortcut. I want to get rid of grams on bottom. I want to get to moles on top. I'm going to be 1 with moles. And my molar mass is how many grams of this stuff, in this case sugar, I have per mole of that stuff, in this case sugar. So my molar mass is given to me as 180.16 grams per mole. So I just have to take 5 times 1 divided by 180.16, and that will give me my moles of sugar in this solution. Let's grab the calculator. and I get, cap off here, 0.0278-ish. Right? And that's moles of sugar. Okay? But I'm not done yet. I still have to convert that into molality. So I'm going to take this 0.0278 moles and divide it by my 0.01 kilograms of water. To get my molality. So last time I checked, 0.0278 divided by 0.01 is going to be 2.78 molal concentration. Okay, well, I was about to circle that, but we're also still not quite done yet. There's a lot to do here. Okay, because we definitely need this, but we still need to figure out how much the freezing point is lowering by. So, one last step. Okay. My depression of my freezing point, my delta TF, is going to be equal to my KF. We're dissolving in water, so again, it's going to be 1.86 degrees C per little m times the 2.78 molal I just calculated. My little m's should cancel out, and I should get my answer. So 1.86 times 2.78. Let's see. Get about 5.17-ish degrees Celsius. Again, if we wanted to take that a step further, since this is how much our freezing point is lowering by, okay, our freezing point of water is typically 0 degrees Celsius. 0 dropping by 5.17 degrees Celsius would leave our new freezing point down at negative 5.17 degrees Celsius. All right, here's our last example. If you've ever used something like driveway heat or other roadway salts where you spill out some stuff onto the driveway, this works not only by releasing heat as they dissolve, especially for calcium chloride, but they can also lower the freezing point of the water. By having that solute dissolved in there, it's going to make it harder for the stuff to kind of coagulate back into the solid form. So it's going to be able to kind of melt at a higher temperature. Okay, so if we have a puddle of water that has dropped its freezing point down from 0 to negative 2 degrees Celsius, we want to calculate the molality that has been made with the solution. So we're working with water, so we can just pick out the KF for that. And since our freezing point has dropped from 0 degrees Celsius to negative 2 degrees Celsius, we can figure out the delta TF for that. In this last example, all that we're given is that our calcium chloride solution, our driveway heat stuff, or roadway salt, is decreasing the freezing point from 0 degrees Celsius down to negative 2 degrees Celsius. So Our change in freezing point, our delta TF, is how much it drops by. So if we're going from 0 to negative 2 degrees Celsius, that means our change in freezing point is 2 degrees Celsius. Okay, that change in the freezing point should also be equal to the Kf for water, that 1.86, times the molality of the solution. So, to solve out, we're just going to divide both sides by this 1.86. We should get our molality alone. Right? Our degree Celsius should cancel out. We should get rid of this whole thing over here. So 2 divided by 1.86 is going to give us our molality. Okay, gotta grab my calculator. I get 1.08-ish. About 1.08 moles per kilogram of water. It's about 1.08 molal concentration. So just remember, if we're not given the delta TF or the delta TB directly, that's just how much your boiling point is increasing by or how much your freezing point is decreasing by.